Welcome back everyone. In this lecture we are going to learn about the basics of morphological image processing, and we'll have some preliminaries of set theory and how we operate image objects as a function of set, binary set, and what are the operations that we can perform. And then we'll understand the concept of translation and reflection on a binary image, and we'll have a brief preview about dilation, erosion, and structuring element. Here we'll just brush up on the concept and what's the idea with the dilation and erosion. The detailed discussion will be done in the next lecture. This is the third part of module 4, morphological image processing. The first question is, what are morphological operations? The term morphological operations come from the word morphing in biology, which means changing a shape. You might have uh, heard about this, or you might have known about this phenomena where a caterpillar morphs into a butterfly. Uh, so the process is a metamorphosis. Something similar to this we are performing on images. So that's why we call it as morphological operations. So image morphological operations are used to manipulate object shapes such as thinning, thickening, and filling. So binary morphological operations are derived from set operations. We'll go through the basics of set operations before we move on to the actual morphological topics, morphological image processing topics. Let us go through some preliminary concepts for set theory, which we will be using in this morphological image processing. So let A be a set in Z square. Here Z square is a Cartesian square of integers, where basically it's a set of all pairs of integers. So if it was R, it means real numbers. Uh, we are only talking about integers here. And A is equal to A1 comma A2 is an element of A, where A belongs to set A. So this is the belongs to notation that you are aware of. And if A is not an element of A, then we write it as A does not belong to A using this symbol. And null empty set is 5. We can express the sets in two types. In the first method, which is called as the roster notation, it is the standard mathematical notation for a finite set, places its elements between a pair of curly braces like this one, which is usual thing we do when we represent a set. We list all the set elements, okay, like this a1 a2 up to an, or any integer or any set member is listed between the curly braces. In the second notation, which is called as a set builder notation, here the set is specified as a selection from a larger set determined by a condition involving the elements. So which looks like this: A is equal to element followed by the condition for the set elements, which is example is C is equal to W, where W is equal to minus D for D belonging to capital D, set capital D. So this is how we uh, write the sub builder notation, and this notation will be using more in this topic. Let's go through some basic set operations. A set is a subset of B. That means every element of A is an element of another set B. That can be denoted as this symbol. A is subset of B. Okay. Next, union. So C is A union of B. This stands for union, this symbol U. And intersection, C is A intersection B. So the common elements in A and B. So the symbol for intersection. And mutually exclusive. So A union A intersection B is a null set. So there are no common elements between A and B sets. So that means it is represented as null set, and it is basically, it means it's a mutually exclusive sets. So let us illustrate this set theory graphically. Uh, we are dealing with images, so concept of a set in binary image morphology is each set may represent one object. It could be a building, it could be a car, it could be a person. So we are dealing with binary images here. So that is the key point we should remember, binary image morphology. So each set may represent one object, and each pixel xy has its status, belonging to a set or not belonging to a set. So only possibilities, it belongs to a set or does not belong to a set. No other options because it's binary. So there are two sets A and B. Now if you consider A union B, so the entire area covered by these two sets are shown. So they are marked as gray. Now for intersection A intersection B, the common area or the overlapping area between set A and B are highlighted here. So this part highlights A intersection B. Okay, so A union means entire area, including the overlapping and the A and B parts objects. And here only the overlapping area. Next, so this is A complement. That is a point which does not belong to set A. So it's basically the inversion. So whichever point which does not belong to A is shaded. The entire A set is left out. And A minus B is you just subtract A from B, and this is what you get. Only this part remains, and this overlapping part is left out. So this is A minus B. So these are some basic graphical examples for set theory. Before we move to the next topic, we'll first understand the basics of translation and reflection. So translation means we are shifting or moving the object along x or y axis as defined in the uh, defined by some expression. So here we are moving this triangle by 1, 2, 3, 4, 5, 6, 7 units to the right along x-axis. This example or illustration is taken by this website. Okay, you can go through that to have a better understanding. One more example. So if you move this with the minus 7 plus 1, you move it by 7 units to the left, and move it by 1 units to the top, okay, up. So from this location plus 6 move to the right, and there is no movement along the y-axis because it's 0. Now plus 1 minus 7, 1 unit to the right and 7 units down, and next it is minus 7 plus 1, 7 units to the left and 1 unit to the top. So this is how the translation works. So next is the reflection part. So reflection, here in the first example we are reflecting this point A with reference to y-axis. So minus 3 2, its reflected part will be plus 3 and plus 2. Okay, so the reflection is along the y-axis here. Okay, and you can again do it along x-axis also. So reference line is x-axis for this. So point A is 2 comma 4. Its reflection along x-axis, if you take x-axis as reference, it will be 2 minus 4. So this is about reflection and translation. So all these examples are taken from this website. So now let's understand translation and reflection operations on a on an image object. So translation is expressed as A of Z, which is the translation magnitude, is equal to C, where C is A plus Z for all A belonging to the set A. So this is the subset A, and when we perform translation, we move the object by Z units here, which is Z1 and Z2 equal along x and y axis. And reflection is expressed as B cap is equal to W, where W is equal to minus B for B belonging to set B. So this is our B, and when it is reflected along x and y axis, we get this one. Okay, so this is what we mean by translation and reflection. Here is one more example of reflection and translation. So this is a set, and its reflection is given as this one, B cap. So this is the set B, and this is reflection B cap, and its translation is this one, B of Z moved by Z uh, coordinates, okay, along x and y axis. Okay, this is about reflection and translation. Let's see some of the logical operations that we can perform on binary images. So these logical operations you are already familiar with, and, or, and not operator, and these relationships are uh, general anyway. Everybody knows this. Now, how it appears on an image, that's we'll examine now, and we are examining only binary images. It doesn't work on other types of images. Only binary images we are considering. So this is image A and B. Now look at the pattern, observe. Okay, so the dimensions are same. Image A has a black spot here, B has a black square here. Next, not of A is inversion of A, so white becomes black, black becomes white. Now A and B, whenever they overlap, that region is kept as black. All other parts are white here. Okay, overlapping part, because it's a AND operator. And OR operator here. So OR is A plus B, basically plus operator. So A plus B, whatever you get, okay, all the regions are darker here. So this is A or B. Next, A XOR B. So this is the exclusive OR. Apply the operator, and you will get this kind of pattern. Okay, so whenever they are matching, you write it as 0. Okay, and other part it is black, and not A and B. So this is the image that you will get. Okay, you can pause the video and try to figure out what exactly happening if you are more interested. Now let us have a brief introduction to mathematical morphology. We'll discuss about all these things in depth in next lecture. So here is just a preview. So there are two basic operations that we do in morphological operations: dilation and erosion, and several composite relations between these two, like closing and opening, and thinning and thickening. So all these operations basically depend on dilation and erosion. What is dilation? The general definition is the action or condition of becoming or being made wider, larger, or more open. Now, how do we do that in a digital image? Okay, so this operation in dilation uh, in digital image basically expands the connected sets of ones of a binary image. So basically, we are making this object larger. This hexagon is made larger. That is basically the dilation. Now, the dilation can be used for growing features like this, growing features or filling holes and gaps. You can see there's a gap here or there is a hole here. So that can be filled using the dilation process. Erosion basically does the opposite of dilation. Uh, Erosion basically removes the boundary elements or erodes away the boundary objects. So the dilation expands or makes the object bigger. Erosion shrinks the object. So erosion shrinks the connected set of ones of a binary image. So you can see here the input image is bigger and it has been eroded at the boundary. And here also the circle has been reduced into a smaller size. So it can be used for shrinking features, removing bridges, branches or protrusions. So like this. So there's a bridge connecting these two circles that can be removed using erosion concept. And also there's a protrusion, you can see here, small object protruding out here. So this thing can be eliminated using erosion. Okay, so we'll have a deeper discussion about erosion and dilation, how exactly it is performed and how to represent it in a set theory, set concept. So all those things we'll discuss in the next lecture. So continuing with erosion and dilation, so these are the basic operations and they are dual to each other. So what we need to remember is erosion shrinks the foreground and enlarges the background. Okay, so the background becomes larger and the foreground becomes smaller with erosion, and dilation is the dual to that. Basically it enlarges the foreground and shrinks the background. One more element that we are going to use for performing erosion and dilation is called structuring element, or also called as kernel. So structuring elements can have varying sizes. Usually element values are 0 or 1 and none. Structuring elements have a origin, and for thinning other values are possible. Empty spots in the structuring elements are don't cares. And the structuring element examples are here. So these are the two types. First one is the box and second one is the disk. Box is we have all the values filled up in a 3x3 kernel, and in a disk only we have the 4 neighborhood and the center pixel. And you can see uh, this is the origin marked in circle here. So this is structuring elements of origin. Okay, and we use this structuring element to move around the objects to perform our morphological operations, dilation, erosion, thinning, thickening, whatever we are going to do are done using the structuring elements. They come in variety of sizes. So if you uh, want to see how it works, here is the example. So there's a this type of structuring elements. So we place the structuring element wherever it makes the contact. It's called hit. We extend that pixel. We replace. We put another pixel at the origin point of this structuring element. So here it is none. Now it is hitting. So we'll put a extend the pixel here. Extend the object. So like this, we'll slide around the uh, edges to dilate the structure. Okay, more about it in the next lecture. So far in this lecture, we have looked at introduction to morphological image processing, preliminaries of set theory, and we looked at translation and reflection operation on a binary image. And we had a preview of dilation, erosion, and structuring element. In the next lecture, we'll discuss about the dilation and erosion concept in detail. See you at the next lecture. Thank you.